Module 2, Lecture B, Autograd with TF. By the end of this lecture, you will be able to use tf.GradientTape to compute gradients of scalar losses with respect to TensorFlow variables, interpret gradient values to understand how parameter changes affect a loss function, and implement a simple manual training step using gradients and an optimizer. Gradient tape essentials, tracing operations. Automatic differentiation works by tracing operations inside a gradient recording context. During this process, the system tracks every differentiable operation on your variables and builds an internal computational graph. This hidden graph describes how the final loss depends on intermediate results and parameters. With this trace in place, the system can apply the chain rule to compute gradients and determine how changes in the variables affect the loss. In automatic differentiation, tracing happens dynamically as your Python code runs rather than being fixed in advance. Each time you start reporting and run a forward pass, the system builds a new trace that follows the actual control flow, including conditionals and loops. Only the operations used for the current batch of data, such as different transformations for low-risk and high-risk transactions, are recorded. When you request gradients, the system replays this trace to see how changes in variables affect the loss, allowing flexible, data-dependent models while still supporting automatic differentiation. When using automatic differentiation, you must perform all differentiable operations while tracing is active, so every tensor operation is recorded in the computational graph. If you do computations outside this context, or convert tensors to regular numbers, those steps are not tracked and their contribution to the gradient is lost. In applications like recommendation systems, this means that pre-processing and combining features must happen during tracing so their effect on the loss is captured. Understanding this timing helps you write training code that produces correct gradients and avoids missing important parts of the computation. Python code. Tracing operations. This script shows how TensorFlow's gradient tape records operations as they run, so you can compute gradients from those traced computations. It highlights that the tracing is dynamic, meaning it captures operations as they happen, rather than relying on a fixed graph. By running the cells, you can observe how gradients are derived from the recorded operations. Overall, it is a simple demonstration of dynamic gradient tracing in TensorFlow. The commented line is a reminder to install TensorFlow version 2.20.0 before running the script. It specifies the exact version needed so the code works as intended. Using a different version could change features or behavior and might cause compatibility problems. Ensuring this version is installed helps the script run correctly and consistently. We begin by importing the ImportLib and sys modules. ImportLib lets us programmatically check whether TensorFlow is available before actually importing it. This is a defensive programming approach that helps prevent the script from crashing if TensorFlow is not installed. The sys module is also imported, mainly for possible use in error handling or system-related tasks, even though it is not directly used in this code snippet. The code uses the import library to check whether TensorFlow is installed by calling a function that looks up the TensorFlow module. If TensorFlow is found, this function returns information about the module. If it is not installed, it returns nothing. This check is important because it confirms that TensorFlow is available before trying to load it. By doing this first, the program avoids runtime errors and can handle the absence of TensorFlow in a controlled way. The script first checks whether TensorFlow is available by inspecting its import information. If TensorFlow cannot be found, it immediately raises an import error with a clear message stating that TensorFlow is required. This early check alerts the user right away about the missing dependency and stops the script from running further, avoiding later execution errors. After confirming that TensorFlow is available, the script imports it so it can be used throughout the program. This import is essential because TensorFlow is the main library for building and running the computational graphs used here. By bringing TensorFlow into the script, you gain access to its tools for machine learning and numerical computation. These tools are required for the gradient tracing operations that the script demonstrates later on. This configuration tells TensorFlow to run only on the CPU and ignore any available GPU hardware. It does this by setting the list of visible GPU devices to be empty. As a result, TensorFlow will not attempt to use CUDA, the GPU-based computing platform, which helps avoid CUDA-related errors. All computations are therefore forced to execute on the CPU. This line displays the version of TensorFlow currently in use, allowing you to quickly verify that the correct library version is installed. Checking the version helps ensure that your code is compatible with the library and behaves as expected. This is especially important when relying on specific features or programming interfaces that can change between TensorFlow versions. We use TensorFlow's random module to set a fixed random seed so that any operations involving randomness give the same results every time the code runs. This makes the behavior of the program consistent across different runs. As a result, experiments and models become reproducible, which is essential for reliable testing and comparison. We begin by defining a scalar variable using TensorFlow's variable class, initializing it with the floating point value 2, and setting its data type to float32 for consistent numerical operations. Giving this variable a descriptive name that indicates it represents a weight clarifies its purpose in the script. This initialization is important because the variable will be involved in operations that TensorFlow tracks for gradient calculations using the GradientTape mechanism. We define a small helper function called showGradients that takes a label and a gradient value, then prints the label followed by the phrase gradient dw equals and the numeric value of the gradient. It converts the gradient to a standard floating point number so it is easy to read. This function is used to neatly display the gradients produced during tracing, helping you quickly interpret the results of the computations. We define a simple scalar loss function that takes an input value and computes the squared difference between the product of a variable and that input and the constant 3. This squared difference measures how far the prediction is from the target value. The loss function will later be used to compute gradients with respect to the variable, so we can see how changing that variable affects the loss. We create a constant tensor with the fixed value of 1.5 and set its data type to 32-bit floating point. This tensor does not change during our experiments. By keeping this input constant, we can clearly see how modifying other variables influences the results of our computations. We use TensorFlow's GradientTape to record the operations needed for automatic differentiation. Inside this context, we tell the tape to watch the parameter we want to update, which is the variable w. We then compute the loss by applying the loss function to the input x, and this calculation is captured by the tape. Because of this recording, we can later compute the gradient of the loss with respect to w. TensorFlow's GradientTape is used here to compute how the loss changes with respect to the variable w. By calling the gradient method on the tape, we obtain the derivative of the loss with respect to w. This tells us the direction and rate at which the loss changes as w changes. That information is essential for optimization, because it guides how we should update w to reduce the loss. We call a function to display the gradient, giving it a label and the computed gradient value. This function prints the label followed by the gradient of the loss with respect to a chosen variable. Seeing this output lets us check that the traced computation is correct. It also shows how changes in that variable influence the loss, which is important for understanding and debugging the optimization process. Using TensorFlow's gradient tape, we trace operations so we can compute gradients later. Inside this context, we explicitly watch the variable w, so any calculations that involve w are recorded for gradient computation. We then compute an intermediate value by multiplying w with x, and this operation is captured by the tape. However, the final loss is calculated after leaving the tape's context, so its gradient with respect to w cannot be computed, showing that operations done outside the tape are not traced. In this example, the loss is calculated outside the tracing context, using an intermediate value that was produced earlier while tracing. We take that stored value, subtract 3 from it, and square the result to get the loss. Because this computation happens after the gradient tape has stopped recording, it is not captured for automatic differentiation. This is done on purpose to show that operations performed outside the tape scope are not traced, and therefore do not contribute to gradient computation. This example shows that TensorFlow can only compute gradients for operations recorded inside a gradient tape context. The code tries to get the gradient of a loss with respect to a variable using a tape that did not record how that loss was computed. Because the loss was calculated outside the tracing scope, the gradient result is none. This highlights that all operations needed for gradient computation must be performed within the gradient tape scope. This example shows that the gradient is printed as none because the computation that produced the loss happened outside TensorFlow's gradient tape context. Since those operations were not recorded by the tape, TensorFlow has no information to use for automatic differentiation. As a result, it cannot compute gradients for that loss. This illustrates that all operations involved in the loss must occur within the tape scope for gradients to be available. TensorFlow's gradient tape lets us dynamically trace operations, so we can compute gradients even when the code has branches. We start by creating a gradient tape context that records operations for automatic differentiation and make sure it is watching the parameter we care about. Then we define a simple conditional. If the input value is greater than 1, the loss is the square of the product of the parameter and the input. Otherwise, the loss is the square of the product of the parameter and the input minus 1. This shows that TensorFlow can follow the actual control flow taken during execution and still compute correct gradients. We now compute the gradient of the loss with respect to the parameter w using TensorFlow's gradient tape. This tells us how sensitive the loss is to changes in w for the specific path of code that actually ran. Knowing this gradient is essential because it indicates how the model parameters should be updated in order to reduce the loss and improve the model's performance. We use a helper function from the dynamic control flow section to display the gradient, which takes a text label and the gradient value and prints them in a clear format. In this example, it shows the gradient that comes from the specific branch of code that ran, based on a condition involving the variable x. This illustrates that TensorFlow's gradient tape can follow and compute gradients through operations even when they depend on conditional control flow. Overall, it helps us see how gradients are correctly associated with the path the program actually executed. This script illustrates how TensorFlow's gradient tape dynamically traces operations so it can compute gradients. It defines a scalar variable and a simple loss function, then shows that when calculations happen inside the gradient tape context, the tape records them and the gradient of the loss with respect to the variable can be computed. When the same operations occur outside that context, the tape does not capture them and the gradient is returned as none. The script also demonstrates that control flow, such as conditional branches, is traced dynamically, so gradients are computed only for the path that is actually executed. Overall, it emphasizes that gradient computation in TensorFlow depends critically on which operations are performed within the gradient tape context. Persistent and non-persistent tapes. In automatic differentiation, operations can be tracked in either non-persistent or persistent mode. In non-persistent mode, the system records tensor operations only long enough to compute gradients once, then discards that history to save memory. This is well suited to typical training loops where you compute a loss, obtain gradients, update parameters, and then move on to the next batch without needing the same computation record again. You can think of it as taking temporary notes just for a single use, then throwing them away once the gradients are computed. In persistent mode, the system keeps the record of operations even after computing gradients, so you can request more gradients for different tenses or analyze how various outputs depend on the same computation. This is helpful when studying complex models or trying different loss functions without rerunning all the calculations. However, it consumes more memory, so you should use it carefully and release resources when you are done. Choosing between persistent and non-persistent modes for gradient computations is about balancing flexibility and efficiency. In most training loops, non-persistent mode is preferred because it uses less memory and keeps computations lightweight. Persistent mode is more useful for tasks like debugging or sensitivity analysis, where you want to reuse gradient information without recomputing it. Understanding this trade-off helps you manage resources effectively while still examining your models in depth when necessary. Python code, persistent and non-persistent tapes. This lesson introduces the basics of using TensorFlow gradient tape. It explains how to compute simple gradients and highlights the difference between non-persistent and persistent tapes. The goal is to give you a clear, focused understanding of how gradient tape records operations and supports gradient calculation in a straightforward way. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the intended library and avoids problems caused by changes in newer or older releases. This practice helps keep behavior consistent when the code is run in different environments. We configure TensorFlow by adjusting a few environment settings. First, we turn off automatic just-in-time compilation, which can cause errors for some operations. Then we disable 1DNN optimizations, so TensorFlow behaves more consistently across different hardware. Finally, we prevent TensorFlow from using the GPU, which helps avoid certain just-in-time compilation issues that occur specifically on graphics processors. We begin by importing the TensorFlow library and assigning it a short alias, pronounced TF. This alias makes it quicker and easier to call TensorFlow functions and classes throughout the script. Using a concise name like this is a common practice because it keeps the code cleaner and more readable. Overall, it helps streamline your work and reduces repetitive long names in your program. This code tries to turn off the XLA just-in-time optimizer in TensorFlow to avoid potential GPU compilation problems. It does this inside a try-except block that calls the TensorFlow configuration optimizer and sets just-in-time compilation to false. If this call fails for any reason, the error is caught and ignored, so the program can continue running. Overall, this step helps the script run more smoothly by reducing the chance of GPU-related compilation errors. We start by printing the version of TensorFlow that is currently in use. This simple check confirms that TensorFlow is installed correctly and that the version matches what our script expects. Verifying the version helps avoid compatibility issues and ensures the code will run as intended. We begin by creating a scalar variable in TensorFlow that holds the value 3, as a floating point number. This variable will act as the input for our gradient calculation experiments. By setting its data type to 32-bit floating point, we make sure it works efficiently and correctly with TensorFlow's built-in operations. The simple loss function takes one input value and computes a loss by squaring that value and then adding 2 times the value to the result. This calculation produces a single numerical output, also called a scalar. In a machine learning context, this kind of function is used to measure how well a model's predictions match the actual data by assigning a numerical loss to each input. We begin by computing the initial value of the loss function using the current value of the parameter w. This simple loss function takes w as input and produces a single numeric output. We then convert this value to a standard floating point number and print it for easier reading. This gives us a clear starting point for the loss before we perform any gradient calculations. We use TensorFlow's gradient tape in its default non-persistent mode, which means it records operations only once and then automatically frees its resources after computing the gradient. Within this context, we compute the loss by applying a simple loss function to the variable w. Because the tape tracks how w is used to produce the loss, we can then calculate the gradient of the loss with respect to w. We use a non-persistent gradient tape to compute the gradient of the loss with respect to the variable w. This type of tape records operations only once and is discarded after the gradient is calculated. Once the gradient is obtained, we convert it to a standard floating point number and print it for easier reading. This illustrates how non-persistent tapes support simple, one-time gradient computations in automatic differentiation. We try to compute the gradient again using a non-persistent tape to show that this type of tape is meant for only one use. When we attempt to reuse it, the system raises an exception. We catch this exception so the program can handle the error without crashing. Finally, we print the exception type to confirm that the error specifically comes from reusing the non-persistent tape. We use TensorFlow's gradient tape in persistent mode so we can compute gradients multiple times without recreating the tape. Within this context, we calculate the loss using a simple loss function that depends on the variable w. This approach is important when we need to access gradients more than once, because it avoids repeating the forward computation each time. Overall, persistent mode makes repeated gradient calculations more efficient and convenient. We begin by using a persistent gradient tape so we can compute gradients more than once without recreating the tape each time. With this tape, we call its gradient operation, giving it the loss function and the variable of interest, which in this case is the weight parameter. This operation returns the gradient of the loss with respect to that weight. Finally, we convert this gradient to a standard floating point number and print it to clearly show the result of this first gradient calculation. We make a second gradient calculation using the same persistent tape, which is possible because persistent tapes support multiple gradient evaluations without being cleared. After computing this second gradient, we convert its value to a standard floating point number and print it for easier reading. This illustrates how persistent tapes are useful when you need to compute gradients more than once for the same recorded operations. We delete the persistent tape to explicitly free up resources. Persistent tapes can use significant memory, so removing them when they are no longer needed is important. This helps keep memory usage under control and ensures resources are managed efficiently. This script shows how TensorFlow's gradient tape computes gradients in non-persistent and persistent modes. It defines a simple quadratic function of a variable and first uses a non-persistent tape to get the gradient once, demonstrating that trying to reuse this tape causes an error because it is single use. It then switches to a persistent tape, which allows multiple gradient calculations from the same recording and produces consistent results each time. Afterward, the persistent tape is deleted to free resources. Overall, it illustrates that persistent tapes are useful for repeated gradient computations, while non-persistent tapes are more efficient when you only need a single gradient. Watching non-variable tensors. In automatic differentiation, the system mainly tracks how a single loss value depends on trainable parameters, which are special variable objects. Real models also use intermediate tensors, such as temporary results or constant inputs, that are not variables but may still need gradients. To get gradients with respect to these regular tensors, you must explicitly mark them to be watched during computation. This tells the system to include them when it calculates how the loss depends on everything involved. When exploring or debugging a model, it can be important to explicitly watch certain tensors so you can track how they affect the loss. For example, in a recommendation system, you might watch user embeddings or item features, even if they are not trainable variables. Marking these tensors to be watched adds them to the computation graph, so you can compute gradients of the loss with respect to them. This makes it possible to run sensitivity analyses, see which inputs most influence predictions, and assess how robust the model is to small changes in the data. When choosing which non-variable tensors to watch, remember that the gradient system only records operations while tracing is active. Any tensor that should have gradients must be available and explicitly marked to be watched before it is used in computations. If you skip this, the tensor is treated as a normal value and no gradient is computed, even if it affects the loss. Plan your computation so important inputs, such as particular images or time steps, are watched at the right time. This gives you precise control over which gradients are available for analysis, without changing the model's architecture or parameters. Interpreting TensorFlow gradients. Gradient tape usage patterns. When using automatic differentiation, it is important to set up the gradient recording context around a single forward pass and loss computation, then immediately request gradients for the parameters you care about. This is like starting to record just before you feed data into the model and stopping right after you evaluate how accurate the prediction is. The resulting gradients tell you how sensitive the loss is to small changes in each parameter for that specific input and loss value. This setup makes it easier to interpret cause and effect, such as how changing a particular weight would influence the loss in a house price prediction task. The tensors you choose to track for differentiation determine how you interpret the resulting gradients. Letting the system automatically watch variables means those are the ones you plan to analyze and update. In contrast, explicitly selecting which tensors to track lets you focus on how particular features or intermediate values influence the loss. For example, in a medical model, you might track a risk score to see its direct effect on the loss. By choosing carefully, gradients become both update rules and diagnostic signals that reveal which parts of the computation graph are most influential. When you use a recording context for gradients, you can apply it once or keep it active, and this choice changes how you interpret the results. In standard training, a single recording of the forward pass, loss, and gradients gives a clear snapshot of how the model behaves. In more complex settings, you might keep recording to see how different objectives, such as accuracy and fairness, respond to the same operations. In this view, gradients act as context-dependent signals that show how parameter updates would move the model toward better performance or more equitable outcomes. Python code, gradient tape, usage patterns. This material introduces basic gradient computation in TensorFlow using the gradient tape feature. It highlights common patterns for recording operations and then computing gradients with respect to chosen variables. As you run the examples, you will see how gradients are calculated and how to interpret their values in simple scenarios. The goal is to build an intuitive understanding of how gradient tape supports automatic differentiation in TensorFlow. The line that begins with an exclamation mark is a shell command to install TensorFlow version 2.20.0. You would run this in a terminal or notebook to make sure that exact TensorFlow version is available so the script can run correctly. In the script, it is commented out, which means it is optional, where that TensorFlow is already installed in the environment. We start by configuring the system so that TensorFlow does not use the graphics processing unit and instead runs only on the central processor, which is helpful when a GPU is not available or not needed. To do this, we adjust an environment setting through the operating system module. We then import TensorFlow, the machine learning library we will use, and print its version number to confirm which release is installed and ensure it matches our requirements. We begin by creating a scalar input tensor in TensorFlow that stores the constant value 2 using the float32 data type. This tensor serves as a basic input to our model. Defining it in this way lets us apply operations to it and later compute gradients with respect to this input during model training or analysis. We begin by defining a trainable variable that represents a weight in our model. It is created with TensorFlow's variable function and initialized to a value of 1, using a 32-bit floating point type so it works smoothly with TensorFlow operations. Because this variable is trainable, its value can be updated during the learning process. We will use this weight in a loss function to show how gradients are used to optimize the model. We define a loss function that takes a weight and an input value and computes a simple quadratic loss. It multiplies the weight by the input, subtracts 3 from that result, and then squares the difference. This squared value measures how far the prediction is from the target value of 3. The function is used to evaluate how well a particular weight predicts the desired outcome, so that we can adjust the weight to reduce this loss. We use TensorFlow's gradient tape to record the operations involved in computing the loss, so that we can later perform automatic differentiation. Inside this recording context, we compute the loss by feeding the current weight and the input tensor into the loss function. This process builds the computational graph that gradient tape needs in order to calculate gradients with respect to the weights during optimization. In this example, TensorFlow's gradient tape is used to compute how the loss changes with respect to a weight. After the loss is calculated, we ask the tape for the gradient using the loss and the weight as inputs. The result is a value that shows how much the loss would increase or decrease if we slightly change that weight. This gradient is essential for optimization because it tells us how to adjust the weight to reduce the loss. The code first prints the loss from a single forward pass, converted to a regular number, so it is easy to read. This loss value shows how far the model's current prediction is from the target. It then prints the gradient of the loss with respect to the weight, also as a regular number. This gradient tells us how the weight should change and by how much to reduce the loss. Together, these values reveal how well the model is performing and what adjustments are needed to improve it. The gradient sign and size tell us how to change a weight to reduce loss. When the gradient is positive, it means we should decrease the weight to lower the loss. When the gradient is 0 or negative, it means increasing the weight will help minimize the loss. This simple rule for interpreting the gradient is essential for guiding how the model's parameters are optimized. The code prints a suggestion for how to change the weight based on the sign of the gradient. A positive gradient means you should decrease the weight to reduce the loss, while a negative gradient means you should increase the weight to reduce the loss. In other words, the direction of the gradient tells you how to adjust the weight to move toward a lower loss value. We create a constant tensor with the value 1.5 using TensorFlow and specify that it has type float32. This tensor is fixed and does not change during training like a variable would. However, we still want to compute gradients with respect to it, so we explicitly tell the gradient tape to watch it. This setup lets us study how changing this feature would influence the loss function, even though the tensor itself is not updated during training. We use TensorFlow's gradient tape to record operations so we can perform automatic differentiation. Because the base feature is not trainable by default, we explicitly tell the tape to watch it. We then compute the loss with a chosen loss function that takes the current weight and this base feature as inputs. This setup lets us later calculate how the loss changes with respect to the base feature, revealing how sensitive the loss is to variations in that feature. We now compute the gradient of the loss with respect to the feature tensor. Because the gradient tape is set to watch this feature, we can call its gradient method to perform this calculation. The resulting gradient tells us how sensitive the loss is to small changes in the feature. This reveals how the feature influences the loss function and helps us understand its role in the model's behavior. We print the gradient with respect to a specific feature to measure how sensitive the loss function is to changes in that input. This tells us how much the loss would increase or decrease if we slightly adjusted the feature's value. By examining this gradient, we gain insight into how strongly that feature influences the model's performance. We set the learning rate to 0.1, which controls how big a step we take when updating the model's weights based on the gradient. This value directly affects how quickly or slowly the optimization process moves through the search space. A smaller learning rate makes more cautious, precise updates and can help with stable convergence. A larger learning rate speeds up training but risks jumping past the best solution. We use TensorFlow's gradient tape to record the operations involved in computing the loss, so that automatic differentiation can be applied. Within this recording context, we evaluate the loss by applying the loss function to the current weight and the input data. This recorded computation then allows us to calculate how the loss changes with respect to the weight. That gradient is what we need to update the model parameters during training. We use the gradient tape to compute how the current loss changes with respect to the weight. This gives us the gradient, which is the slope of the loss function at the current weight value. Knowing this slope is essential because it tells us how to adjust the weight to reduce the loss. In other words, the gradient guides how we update the weight to improve the model's performance. In this step, we apply a basic gradient descent update to the model's weight. We take the current weight and subtract the learning rate multiplied by the training gradient. This moves the weight in the direction that reduces the loss. The result is the new updated weight after one gradient descent step. We first print the current value of the weight to see our starting point before any learning happens. Then we print the gradient of the loss with respect to this weight, which tells us how sensitive the loss is to small changes in the weight. Finally, we print the new weight after taking a gradient descent step, showing how it has been adjusted in a direction that should help reduce the loss in future updates. After updating the weight, we calculate the new loss by feeding the updated weight and the input into the loss function. We then compare this new loss to the loss value from before the update. By printing both values, we can see whether the loss has decreased. A lower loss after the update indicates that the weight change has improved the model's performance. This script shows how to use TensorFlow's gradient tape to compute gradients for a simple quadratic loss. It defines a constant input, a trainable weight, and a loss based on how far the product of the weight and input is from a target value of 3. Gradient tape records the forward pass and then calculates the gradient of the loss with respect to the weight, indicating whether the weight should increase or decrease to reduce the loss. The script also demonstrates how to explicitly watch a non-trainable tensor to measure how sensitive the loss is to changes in that value. Finally, it performs a manual gradient descent update on the weight and confirms that the loss decreases, illustrating a basic training step. Multiple variable gradients. In models with many parameters, the gradients are not a single number but a structured collection that mirrors the layout of all the trainable parts, such as weights and layer parameters. TensorFlow gives you a separate gradient for each of these parts, showing how sensitive the loss is to small changes in that specific parameter while the others stay fixed. Together, these gradients describe the local shape of the loss function around the current parameter values. By looking at their sizes and signs, you can determine how to adjust the model parameters to move in a direction that reduces the loss. Consider a model that predicts house prices using features like size and age, each with its own weight. After training, a large positive gradient for the size weight means that increasing this weight would increase the loss, so the optimizer will push it downward. A small negative gradient for the age weight means that slightly decreasing this weight would increase the loss, so the optimizer will nudge it upward instead. By looking at the size and sign of these gradients, you can see which parameters strongly influence the loss and which have a weaker effect at this point in training. In complex models like deep neural networks, gradients are organized to mirror the model's parameters, so interpreting them is largely about spotting patterns. Smaller gradients in early layers and larger ones in later layers can show that learning is focused on higher-level features. When certain parameter groups have especially large gradients, it suggests the model relies heavily on those components to reduce loss. By examining these gradient patterns, you can see how learning is distributed across the model and detect issues such as vanishing or exploding gradients that may block further improvement. Python code, multiple variable gradients. This script demonstrates how to work with gradients of multiple variables using TensorFlow's gradient tape. The main goal is not the code itself, but learning how to read and interpret the gradient values it produces. By examining these gradients, you can better understand how changes in each variable affect the output of a computation or model. The commented line recommends installing TensorFlow version 2.20.0 to match the needs of the script. Using this exact version helps ensure that all required features and behaviors work as expected. Specifying a library version like this is a common way to prevent problems that can arise when newer versions introduce changes. We start by importing TensorFlow, a major library used for numerical computation and machine learning. After that, we check and print the TensorFlow version currently in use. Knowing the version is important because different versions can offer different features, improvements, or behaviors. This helps ensure that our code is compatible and that we understand which capabilities are available in our environment. We first import the operating system module so we can work with environment variables, and then set the CUDA visible devices variable to -1. This tells TensorFlow not to use any GPUs and to run only on the CPU. Doing so prevents a specific runtime error related to CUDA, the software layer for GPU acceleration. As a result, the script can run smoothly without encountering GPU-related issues. We set a fixed random seed in TensorFlow using the value 42, so that all random operations produce the same results every time the code runs. This makes the behavior of the program predictable and repeatable. Such reproducibility is important for debugging and for reliably comparing experimental results. We define a trainable scalar variable using TensorFlow, initialized to the value 0.5 and stored as a 32-bit floating point number. This variable represents a parameter that the model can adjust during training to help reduce the loss. Because it is marked as trainable, TensorFlow will automatically compute gradients with respect to this parameter. This gradient information is then used by optimization methods such as gradient descent to update the variable and improve model performance. We define a variable to represent the weight for age in our model and initialize it with a value of -0.3, which sets its starting influence on the model's predictions. This variable is stored as a 32-bit floating point number to work smoothly with TensorFlow operations. With this setup, we can later compute gradients for this weight and update it during training as the model learns from data. We use TensorFlow to create a small batch of feature data as a 2x2 array, where each row is a data point and each column is a feature. The first data point has values 80 and 5, and the second has 60 and 20. These values are stored as 32-bit floating point numbers. This simple setup serves as example input for a machine learning model, so we can test how it processes and learns from the features. We create a constant tensor that stores the target prices for our batch, using the values 300 and 180. Each value is placed in its own list so the tensor has the correct shape for later matrix operations. We also set its data type to 32-bit floating point to keep it consistent with the other tensors used in the computation. We combine the two scalar variables for size and age into a single vector using the TensorFlow stack function, so we can treat them as one object. This makes it easier to use them in operations like matrix multiplication within the prediction function. By stacking them, we prepare these variables for efficient computation and ensure they line up correctly with the feature data for later calculations. We first check that the number of features matches the number of weights by comparing their dimensions. The feature data has a second dimension that tells us how many features there are, and the weight vector size tells us how many weights we have. These must align so that later matrix multiplications are valid and meaningful. Doing this check helps avoid runtime errors and ensures the model's predictions are computed correctly. We define a prediction function that takes a batch of input features and a weight vector and uses them to compute output values. Inside this function, TensorFlow performs a matrix multiplication between the feature batch and the weight vector. Before the multiplication, the weight vector is reshaped into a column so it has the correct dimensions. The result of this operation is a set of predictions based on the given features and the current weights. We use TensorFlow's automatic differentiation by recording operations with GradientTape, explicitly tracking the variables for size and age. These variables are combined into a single weight vector that the prediction model uses with the input features to produce predicted prices. We then compare these predictions to the actual prices to compute errors, square those errors, and average them to obtain the loss. This loss value tells us how far our predictions are from the true values and will guide how we adjust the weights to improve the model's performance. We use TensorFlow's GradientTape to compute how the loss changes with respect to the variables for size and age. This tells us how sensitive the error is to each variable and shows how changes in them affect the loss. With these gradients, we know the direction and size of the adjustments needed for each variable. This information guides the optimization process, so we can update the variables to reduce the loss and improve our predictions. We start by printing the current values of the parameters, which are the weights for size and age, so we can see our starting point before any updates. Next, we print the loss value, which tells us how far our predictions are from the actual target values. This loss serves as a measure of the model's current performance and shows how well the weights are capturing the relationship between the features and the targets. We look at the gradient for the size variable to see how much the loss changes when size changes, and then do the same for the age variable. These gradients tell us how sensitive the loss function is to each variable. By comparing them, we can see which variable has a stronger effect on the loss and use that information to adjust the variables in a way that helps minimize the loss. We choose a small step size, such as 0.01, to control how much we change our parameters at each update. Then we adjust the parameter for size by moving it a small amount in the opposite direction of the gradient of the loss with respect to size. We do the same for the parameter representing age, subtracting a small multiple of its gradient from its current value. The signs of these gradients tell us which direction to move each parameter so that the loss decreases over time. In this manual gradient descent step, we update the model's weights using their gradients. We adjust the size weight by subtracting the step size multiplied by the gradient of the loss with respect to the size weight. We do the same for the age weight, subtracting the step size times its corresponding gradient. After these updates, we print the new size and age weights to observe the effect of this gradient descent step. The code prints the absolute values of the gradients for each variable so we can see which feature has the strongest effect on the loss. Using absolute values lets us compare gradient magnitudes directly without worrying about whether they are positive or negative. The larger the absolute gradient, the more that variable influences the loss. This helps us decide which variables to focus on when making adjustments during optimization. This material explains how to use TensorFlow's gradient tape to compute gradients for more than one trainable variable at the same time. It defines two weights for size and age, uses them to predict prices from a small batch of features, and measures error with mean squared loss. Gradient tape then calculates how this loss changes with respect to each weight, and the script prints the initial weights, the loss, and the resulting gradients. A single manual gradient descent step updates each weight by moving it opposite to its gradient, scaled by a small step size. Finally, the script compares the sizes of the gradients to see which feature has a stronger effect on the loss, illustrating how gradient direction and magnitude guide optimization. Handling none gradients. When a gradient is reported as none in automatic differentiation, it is not an error, but a sign that TensorFlow cannot connect that parameter to the loss in the current computation. This means the parameter does not influence the loss, so no gradient can be computed for it. None is different from a zero gradient because it indicates that the parameter is not part of the differentiable path at all. Recognizing this helps you adjust your model so that all intended parameters actually affect the loss and receive gradients during training. It is important to distinguish between a none gradient and a zero gradient. A zero gradient means the loss does depend on that parameter, but at the current value, small changes do not change the loss, such as at a local minimum. A none gradient means there is no differentiable path connecting the loss to that parameter at all. For example, in a recommendation system, if a feature is never used in the scoring step, the loss has no way to depend on it, so its gradient is none. In that case, gradient-based optimization cannot update that feature because there is no information about how changing it would affect performance. Understanding and managing none gradients is important for detecting model design problems and making sure training works correctly. If a parameter that should be trainable always has a none gradient, it usually means it is not involved in the loss calculation, or it passes through non-differentiable operations. This often happens when tensors are converted to plain numbers too early, or when control flow breaks the gradient path. In real applications, such as financial or medical models, Unnoticed non-gradients can leave parts of the network untrained. By correctly interpreting these none values, you can adjust the model so all parameters influence the loss through differentiable operations, and learning can proceed effectively. Python code, handling none gradients. This script demonstrates how TensorFlow can produce gradient values that are set to none, and shows how to interpret those gradients safely. Its main goal is to help you understand what these missing gradients mean and how to reason about them correctly. You are encouraged to run each section of the script and pay attention to the printed explanations. By doing so, you will build a clearer, more reliable understanding of TensorFlow gradient behavior. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the code behaves as expected and remains compatible with any version-specific features or known issues. You typically run this command in a terminal or notebook before running the rest of the script so that the required library is properly set up. We begin by importing the TensorFlow library and assigning it a short, convenient name. This shorter name makes it easier to call TensorFlow functions and classes throughout the program. Using a simple alias helps keep the code cleaner, more readable, and more efficient to write. To avoid runtime errors related to CUDA, this code turns off GPU use in TensorFlow by making the list of visible GPU devices empty. As a result, TensorFlow is forced to run only on the CPU. This approach prevents potential problems that might occur when handling the GPU during execution. We begin by printing the TensorFlow version in use. This step helps confirm which version is running so we can check compatibility. Knowing the version is important because different releases may support different features. It also helps explain any differences in behavior you might see when running code on another system. We begin by defining a scalar variable in TensorFlow that will be used in our gradient calculations. This variable is initialized with the numeric value 2.0 and is assigned the data type of 32-bit floating point. Setting it up in this precise way is important because it ensures the variable can participate correctly in the gradient computations that follow in the script. In this example, we define a TensorFlow variable with an initial float value of 5, but we do not use it in any later computations. The purpose of creating this unused variable is to show how TensorFlow treats variables that do not affect the loss function. Because the variable has no influence on the loss, TensorFlow does not compute a gradient for it. This situation illustrates the idea of a none gradient, which means no gradient is available for variables that do not contribute to the loss. We start by creating a simple input tensor using TensorFlow's constant function. This tensor holds the numeric value 3 and is stored as a 32-bit floating point type. It serves as a basic input that will be used in later calculations, including gradient operations and loss computation. Defining this tensor establishes the initial value that the rest of the model's computations will depend on. We begin by using TensorFlow's GradientTape to record the tensor operations that follow, so we can later compute gradients automatically. Within this context, we instruct the tape to watch both variables, one that will affect the loss and one that will not. By doing this, we set up the system to measure how changes in each variable could influence the loss function. This highlights that GradientTape can track multiple variables, even if some of them ultimately do not impact the final result. In this part of the code, we compute a value called y by multiplying a variable that represents the weight in use with a constant. This product is important because it directly feeds into the loss calculation. Since the loss depends on this result, the weight variable will have a numerical gradient when we perform gradient computation. This step shows how changing the weight affects the overall loss. The code computes a single loss value by subtracting 10 from the value of y and then squaring the result. This squared difference measures how far y is from the target value of 10. It serves as an error signal that the optimization process will try to reduce. By minimizing this loss, the model is encouraged to make y as close to 10 as possible. We use TensorFlow's gradient feature to compute how the loss changes with respect to both variables, the one that is used and the one that is unused. This method tracks how variations in each variable influence the loss value. The output is a set of gradients, one for each variable, indicating how sensitive the loss is to changes in that variable. These gradients guide how the variables should be adjusted during optimization. We separate the gradients into two variables to make their roles clear. One variable stores the gradient of the loss with respect to the weight that actually affects the loss. The other variable is meant to store the gradient with respect to a weight that does not affect the loss. In this case, we expect that second gradient to be none, which confirms that the unused weight has no influence on the loss. This separation makes it easier to inspect and work with each gradient individually. We verify that the gradient of the variable used in our computation is a single scalar value by checking its shape. If the shape does not match a scalar, an assertion error is raised with a message stating that the gradient must be scalar. This check helps ensure that our gradient calculations are correct and that the variable influencing the loss function is producing a valid, properly shaped gradient. We check that the gradient for the unused variable is actually set to none, which confirms that this variable does not affect the loss. If the gradient were present instead, it would mean our understanding of how the computation graph is built is incorrect. By asserting that the gradient is none, we protect the integrity of our gradient tracking logic and ensure that only variables that truly influence the loss receive gradients. We print the gradient value for the variable involved in the computation because it directly affects the loss function. This gradient is a single numeric value that shows how changes in the variable influence the loss. By converting the gradient to a floating point number, we make sure it is in a clear, standard numeric format that is easy to read and display. The gradient for the variable w used is a single numeric value because this variable directly affects the loss. The loss is calculated using w used, so any change in w used produces a measurable change in the loss. This direct influence makes its gradient a concrete number, rather than a more complex structure. In short, since the loss depends on w used, its gradient is a specific numeric value. When we check the gradient of a variable that was not used in the computation of the loss, TensorFlow returns a value of none. This happens because that variable has no effect on the loss, so there is no gradient to compute. This behavior confirms that TensorFlow correctly detects when a variable does not contribute to the loss, and instead of giving a zero gradient, indicates the absence of a gradient with none. The message explains that the gradient for a certain variable is reported as none because that variable never affects the loss. Since it does not play any role in computing the loss, the system does not bother to calculate a gradient for it. This means the gradient is not a numerical zero. It is simply absent. The key idea is that gradients are only computed for variables that actually influence the loss. We first record the current loss as a floating point number to create a clear baseline for comparison. Converting the loss to a precise numeric value lets us reliably refer back to it later. This baseline is essential for showing that changing the variable called w unused does not alter the loss. By comparing the initial recorded value to the loss after modifying w unused, we can demonstrate that the loss remains unaffected. In this example, The variable called w_unused is manually set to 100. But this change does not affect the loss calculation because that variable is never used in computing the loss. As a result, it has no influence on the outcome of the model's optimization. This illustrates the idea of unused variables in gradient calculations, whose gradients are reported as none since they do not participate in the loss function. To check that changing the unused variable does not affect the loss, we create a new gradient tracking context and make sure both variables are being watched again. We then recompute the output using only the variable that actually participates in the calculation, multiplying it by the input tensor. From this output, we form a new loss by taking the squared difference between the output and the value 10. Because this mirrors the earlier computation and still ignores the unused variable, the loss remains the same, even if that unused variable has been modified. We first print the loss value before changing the unused parameter to establish a baseline. After we modify this unused parameter, we can compare the new loss to the original value. Seeing that the loss does not change shows that this parameter does not actually affect the loss function. This confirms that it is not involved in the computation of the loss. When we print the loss after changing the unused variable, we see that the loss value stays the same. This shows that modifying a variable that does not influence the loss has no effect on the loss calculation. As a result, the gradient for this unused variable is none, because the loss does not depend on it. This reinforces the idea that only variables that actually affect the loss will have meaningful gradients. This material explains how TensorFlow handles gradients when some variables do not affect the loss. It uses two scalar variables, one that is part of the loss calculation and one that is not, and tracks them with the gradient tape. The variable that influences the loss receives a numeric gradient, showing its effect on optimization, while the unused variable gets a gradient of none, meaning it has no impact. Changing the unused variable does not change the loss, so its gradient remains none. This behavior shows why it is important to know which variables actually contribute to the loss when building and optimizing machine learning models. Manual gradient training using Keras optimizers. Keras optimizers form the link between raw gradients and effective learning during training. After you compute the gradients of the loss with respect to the model's parameters, the optimizer uses these slopes to decide how to adjust the parameters. It can incorporate features like momentum and adaptive learning rates to make updates more stable and efficient. In this way, gradients provide the direction to reduce loss, and the optimizer controls how large and sophisticated each step toward better performance will be. Keras offers several optimizers, each using a different strategy to update model parameters during training. Simple optimizers use a fixed learning rate to scale gradients, while more advanced ones adjust learning rates based on past gradients. These differences can lead to faster convergence and better accuracy in tasks such as predicting housing prices or classifying images. By choosing a Keras optimizer, you rely on these built-in strategies so you can focus on designing your model while the optimizer handles how the parameters are updated. In a manual training loop, using a Keras optimizer gives you direct control over how the loss is computed, how operations are tracked for automatic differentiation, and how gradients are obtained and applied. This control is important for experimentation because it lets you inspect gradients, adjust them if needed, and log useful diagnostics. For example, in financial forecasting, you might monitor whether gradients are large, indicating aggressive updates, or whether they shrink as the model stabilizes. By combining this insight with the flexibility of Keras optimizers, such as tuning the learning rate, you can refine your training process and better understand how gradients, update rules, and learning dynamics interact over time. Python code using Keras optimizers. This material demonstrates how to manually train a simple regression model using TensorFlow's gradient tape while focusing on how Keras optimizers update trainable variables. It walks through using the gradient recording mechanism to compute gradients, and then applying an optimizer to adjust the model's parameters. The main goal is to show the connection between gradient computation and the optimizer's role in updating weights during training. The script starts by checking that TensorFlow is installed, because this library is the foundation for building and training the machine learning models used in the code. It recommends using version 2.20.0 to keep the environment stable and compatible. Making sure the correct version is installed is an essential setup step before running the rest of the program. We begin by importing TensorFlow and NumPy, two core libraries used for numerical computations and building machine learning models. Before doing so, we set an environment variable that disables access to GPU devices, forcing the program to run only on the CPU. This setup is useful when debugging or when no GPU resources are available. After this configuration, TensorFlow and NumPy are imported and ready to be used throughout the rest of the script. We set deterministic seeds for both TensorFlow and NumPy so that any random operations give the same results every time the code runs. Using TensorFlow's random seed with the value 7 controls randomness in TensorFlow operations, and using the same seed value in NumPy makes its random numbers consistent across runs as well. This reproducibility is crucial for experiments, debugging, verifying results, and sharing code, because it ensures that others can obtain exactly the same outcomes. This line displays the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and running. Confirming the version helps ensure that the rest of the code is compatible with the TensorFlow environment. We create simple synthetic data to model a linear relationship. First, we generate 8 evenly spaced numbers between -1 and 1 to use as input values. Then we define the outputs by multiplying each input by 3 and adding 2. This produces target values that lie on a straight line, described by the rule y equals 3 times x plus 2. We begin by converting our synthetic data into TensorFlow tensors so it can be used in TensorFlow operations. The input data is reshaped into a column vector and turned into a TensorFlow constant, giving it the right form for matrix calculations. The target data is treated the same way, reshaped into a column vector and converted into another constant. This alignment of input and target tensors is essential for performing correct element-wise operations during training. Before training begins, the code checks that the input and target tensors have matching shapes so that every input has a corresponding target value. This is crucial for the training process to work correctly. An assertion is used to enforce this, and if the shapes do not match, it immediately raises an error and stops execution. This early check helps maintain data integrity and prevents runtime errors during model training. We begin by defining 2 trainable variables that the model will adjust during learning. The first is a weight, initialized with random values from a normal distribution, so training does not start with a built-in bias. The second is a bias term, initialized to 0 as a neutral starting point. Together, these variables are updated during training to reduce the difference between the model's predictions and the actual target values. This function computes the mean squared error loss by first finding the difference between the predicted values and the target values. It then squares these differences and uses TensorFlow's reduce mean operation to average them. The result is a single number that represents the average squared difference between predictions and targets, which indicates how closely the predictions match the true values. We use a Keras optimizer based on stochastic gradient descent, or SGD, with a small learning rate of 0.1. A small learning rate makes parameter updates more gradual and helps the training process converge more stably. During training, this optimizer adjusts the model's trainable variables, such as the weight and bias, to reduce the loss function over time. In this training step function, we use TensorFlow's gradient tape to automatically track operations on the model's weight and bias variables. We compute predictions by combining the input data with these variables, then calculate the loss using a mean-squared error function that compares predictions to the true targets. Gradient tape then provides the gradients of the loss with respect to the weight and bias. Finally, the optimizer uses these gradients to update the variables to reduce the loss, and the function returns both the loss and the gradients. We run a loop for 5 training steps, and in each step we call the training function with our data. This function returns the current loss and the gradients for the weight and bias. We separate these gradient values into clear variables and then print the step number, the loss, and the gradients. This printed information lets us track training progress and see how the model parameters change over time. At the end of the script, the program prints the learned weight and bias after training. It first converts these TensorFlow tensors to NumPy arrays so their single numeric values can be extracted, then casts them to regular floating point numbers for a clean display. The printed values are then compared to the true parameters used to generate the synthetic data, which are a weight of 3 and a bias of 2. Seeing how close the learned values are to these true values helps confirm that the training process worked effectively. This script shows how to manually train a simple linear regression model in TensorFlow using a Keras optimizer. It uses synthetic data where the target value is 3 times the input plus 2 and starts with random weight and 0 bias. With gradient tape, it computes the mean-squared error loss and applies stochastic gradient descent with a learning rate of 0.1 to update the parameters. Over several training steps, the loss decreases and the weight and bias move toward the true values of 3 and 2, capturing the underlying relationship in the data. Applying gradients to variables. After computing gradients, the next step is to use them to update the model's parameters so it can learn. Each parameter acts like a control setting, and its gradient shows how changing that setting will affect the loss. If the gradient is positive, increasing the parameter increases the loss, so the optimizer moves it in the opposite direction, and a negative gradient leads to the reverse adjustment. In manual training, you pair each parameter with its gradient and pass them to an optimizer, which updates the parameters according to its rules. Keeping gradients and parameters separate lets you inspect or modify the gradients before applying them, giving you fine control over the learning process. In a learning system, each parameter is like a control setting in an industrial process. After running the system, we measure how far the output is from the target and compute how sensitive this error is to each parameter, which is similar to finding gradients. The optimizer then uses this gradient information to adjust each parameter in a direction that reduces the error. These adjustments are scaled by a learning rate, which controls how large or small each change is. By repeatedly making these small guided updates, the model gradually moves toward parameter values that lower the loss. When we apply gradients to model variables, we are not just updating numbers but can also add useful logic to improve learning. For example, we might shrink very large gradients, skip updates for frozen parameters, or combine gradients from several small batches to act like a larger batch. After these adjustments, the optimizer uses the processed gradients to update each variable, and the new values are used in the next forward pass. Repeating this cycle of computing and applying gradients allows the model to gradually refine how it captures patterns in the data. Python code, applying gradients to variables. This lesson demonstrates how to apply gradients directly to model variables using TensorFlow's GradientTape. It focuses on manually updating parameters rather than relying on built-in training loops. The example is a very small linear model, and the script walks through a single training step to show how gradients are computed and used to adjust the model. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this specific version makes sure the script runs with the expected features and remains compatible with the rest of the code. This is especially important because machine learning libraries change often and can break older code. You typically run this command in a terminal or notebook before running the rest of the script, so the required package is properly set up. We begin by importing the TensorFlow library and giving it a short alias, pronounced tf. This alias makes it quicker and easier to call TensorFlow's functions and classes throughout the script. Using a concise alias for a library with a long name is a common practice that helps keep code cleaner and more readable. We configure TensorFlow to run only on the CPU by telling it that no GPU devices are available. This forces all computations to use the CPU and helps avoid CUDA-related errors when the GPU is not properly set up or supported. It is especially useful in environments with limited or unreliable GPU resources, or when you want the code to behave consistently across different machines. We begin by printing the TensorFlow version being used so we can confirm the environment is correctly set up. Different TensorFlow versions may offer different features or behave differently, so knowing the exact version is important. Seeing the version number helps with compatibility checks and makes debugging easier. This simple step ensures the code is running under the expected conditions. We set the random seed in TensorFlow to a fixed value, such as 42, so that any random operations behave the same way every time we run the code. This makes the model's behavior consistent across runs. As a result, our experiments become reproducible, which is essential during development and testing. We begin by creating a small synthetic dataset that follows a simple linear pattern. Each input is a single floating point number arranged in a column, and these inputs are used to model the relationship where y is 3 times x plus 2. The input values range from 0 to 3, giving us a clear and straightforward set of points. This makes it easy for the model to learn and demonstrate how it fits a basic linear relationship. We use TensorFlow to create a column vector of target outputs that holds the true values we want the model to learn. Each element in this vector is a floating point number that matches the expected output for our synthetic data, which follows a linear pattern where y is 3 times x plus 2. This target vector serves as the ground truth during training and is essential for computing the loss by comparing the model's predictions to these correct values. We create a trainable weight by initializing it with a random value drawn from a normal distribution using TensorFlow. This weight is defined as a 1-by-1 matrix, which means it is just a single scalar value. During training, the learning process adjusts this weight to reduce the loss. As the loss decreases, the model's predictions become more accurate. We create a trainable bias using TensorFlow's variable class and initialize it to 0, so it starts with no offset. Its shape is set to a single value, meaning it is just one scalar. During training, this bias is updated along with other parameters to help the model better fit the data. We use the stochastic gradient descent optimizer from TensorFlow's Keras module because it is simple and effective for small problems. The learning rate is set to 0.1, which controls how big each update step is during training. A smaller learning rate leads to more gradual changes in the model's parameters, and helps avoid skipping past the best solution. We define a model function that takes an input and computes the output of a linear model. It does this by multiplying the input by a weight and then adding a bias term. In this setup, the weight acts like the slope of a line and the bias acts like the intercept. Together, they describe a straight line relationship that we use to make predictions from the input data. Mean squared error loss measures how far a model's predictions are from the target values. To compute it, we take the difference between each prediction and its corresponding target, square these differences, and then average them. The result is a single number that represents the average squared error across all predictions. This metric is widely used in regression because squaring the errors penalizes larger mistakes more strongly. We start a manual training step by using TensorFlow's gradient tape, which records the operations needed for automatic differentiation. Within this recording context, we feed the input data through the model to compute predictions. The model uses its current weight and bias values to produce these outputs. This process builds the computational graph that will later allow us to calculate gradients for learning. In this step, we compute a single loss value by comparing the model's predicted outputs with the true target values. We use the previously defined loss function, which measures the mean squared error between them. This loss tells us how closely the predictions match the actual data and serves as a key signal for how the model should be improved during optimization. We collect the trainable variables such as the weight and bias into a single list so they are easy to manage during training. Grouping them this way lets us pass all parameters at once to functions that need them. This is useful when computing gradients and when applying updates with an optimizer, since those operations must access and modify all trainable parameters together. We use TensorFlow's gradient tape to compute how the loss changes with respect to each trainable variable. Gradient tape records the operations in the model, so it can automatically calculate these gradients. The gradients indicate how each variable should be adjusted to reduce the loss, which directs the optimization process during training. We first verify that the gradients are not missing and that their number matches the number of variables. Each variable must have its own gradient so it can be updated correctly. If the counts do not match, we raise a runtime error to indicate a problem in the gradient computation. This validation step helps catch issues early and prevents incorrect updates during optimization. We pair each gradient with its corresponding variable by combining the list of gradients with the list of variables into matching pairs. This creates a list of gradient variable tuples, where each gradient is directly linked to the variable it should update. This pairing is essential because it tells the optimizer exactly which gradient to apply to which variable during the update step. Without this mapping, the optimizer would not know how to correctly update the model's parameters. The optimizer uses the computed gradients to update the model's variables. It calls its apply gradients method, which takes each gradient paired with its corresponding variable. Using this information, it adjusts the variables in the direction that reduces the loss. This completes one step of the optimization process. We print the loss value after a training step to see how well the model is learning. This loss is a single number that measures the mean squared error between the model's predictions and the true outputs. Converting the loss to a simple floating point number makes it easier to read and interpret. Monitoring this value over time helps us track the model's progress and effectiveness during training. We now print the updated value of the weight by first converting it from a TensorFlow tensor into a NumPy array so we can read its contents. Because this array is two-dimensional, we take the first element, to obtain a single scalar value. We then convert this scalar to a standard floating point number so it can be displayed clearly and concisely. After each training step, we print the updated bias value to see how it has changed due to the gradient update. We first convert the TensorFlow variable that stores the bias into a standard NumPy array. Then we take the first element of this array and cast it to a regular floating point number, so it is easy to read. This simple display lets us clearly observe how training is affecting the bias. We use a constant tensor with the value 4 as a fixed test input to evaluate the model after its parameters are updated. Because this input never changes during computation, any difference in the model's output must come from the training step itself. This lets us clearly see how the training process affects the model's ability to make predictions on new data. Now we use the updated parameters to make a prediction. We run the model on a test input with the value 4, so it uses the new weight and bias to produce an output. This predicted value shows how the model behaves after training and lets us check how well it has learned from the training step for a new input it has not just seen in the update. The code uses the updated model to make a prediction for the input value 4 and then formats that result for easy reading. It converts the model's output from a TensorFlow tensor into a NumPy array, takes the first value, and turns it into a standard floating point number. This final numeric prediction lets you clearly see how the model's output has changed after the training step updated its weights and bias. This script shows a simple linear regression training step in TensorFlow for learning a relationship where the output is 3 times the input plus 2. It defines a model with a weight and a bias, both starting from random values, and uses TensorFlow's GradientTape to compute how the mean squared error loss changes with respect to these parameters. Using these gradients, it updates the weight and bias with stochastic gradient descent and a small learning rate. The script prints the initial loss, the updated parameter values, and then uses the trained model to predict the output for an input of 4, illustrating how the model improves its predictions from the data. Stabilizing gradient behavior. When you update model parameters using gradients and an optimizer, a major issue is keeping training numerically stable. In theory, you just compute the gradient of the loss and update each parameter. But in practice, those gradients can become extremely large or extremely small. Very large gradients can make the loss explode and cause training to diverge, while very small gradients can slow learning to a crawl. Stabilizing gradients means choosing updates that are strong enough to make progress, but not so large that they are destructive, so the loss decreases steadily instead of oscillating or blowing up. Choosing and tuning the optimizer, especially its learning rate, is essential for keeping gradients stable during training. The learning rate controls how big each update step is along the gradient, so if it's too high, the model can overshoot good solutions, and if it's too low, training becomes very slow. In a task like predicting housing prices, you might begin with a cautious learning rate and then adjust it based on how the loss changes over time. Some optimizers also use momentum or adaptive scaling to smooth out noisy gradients and help maintain steady, reliable progress. To keep gradients stable during training, you can limit their maximum size with gradient clipping, which helps prevent instability, especially in tasks with long sequences. It is also important to monitor gradient norms, so you can spot exploding or vanishing gradients early and adjust settings if needed. Revisiting your model architecture or data preprocessing, such as normalizing inputs, can further support healthy gradient ranges. Combined with a well-tuned optimizer, these techniques help ensure each gradient step is stable and leads to reliable learning. Python code. Stabilizing gradient behavior. This script demonstrates how to stabilize gradient behavior during training. It uses TensorFlow's gradient recording tool to perform manual parameter updates. The main focus is on comparing training runs with gradient clipping to those without it, so you can hear how clipping affects the stability of the learning process. The line that begins with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. It is meant to be run in a terminal or notebook, so the script uses this exact version. This matters because different TensorFlow versions can change features and behavior, which can affect how the code runs. Ensuring the correct version is installed helps the script execute properly and consistently. We begin the script by importing a few standard Python libraries. We use the operating system library to interact with the system, for example, to work with environment variables. We import the random library to generate random numbers, which is helpful for setting seeds and making results reproducible. We also include the math library, which provides mathematical functions and constants, even though it is not strictly needed yet and is mainly there for possible future use. This code disables the GPU by setting a specific environment variable so that TensorFlow runs only on the CPU. The main goal is to avoid CUDA-related errors that can occur in some systems when using the GPU. By forcing all computations onto the CPU, the program can run more reliably in environments where GPU support is unstable or problematic. We import TensorFlow to work with tensors and compute gradients, which are central tasks in machine learning. This library provides the core tools for building and training models. It supports automatic differentiation and efficient gradient descent, making it easier to optimize model parameters. We set the random seed to a fixed value using the random library so that any random numbers generated are the same every time the script runs. This makes the results reproducible, which is important for debugging and verifying how the code behaves. By fixing the seed, we can reliably repeat experiments and compare outcomes across different runs. We set the random seed in TensorFlow to a fixed value, such as 7, so that any random operations produce the same results every time the code runs. This makes our experiments reproducible, meaning we can reliably repeat them and get consistent outcomes. As a result, the behavior of our model during development and testing can be replicated and compared over time. This line displays the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and running. Confirming the version helps ensure that the rest of the code is compatible with the TensorFlow environment. We use TensorFlow to create a simple synthetic input data tensor, which is a two-dimensional array with 4 rows and 1 column. This array holds the floating point numbers from 1 to 4. Such a tensor serves as a basic stand-in for real input data. It lets us test how a model processes and learns from these values during training, without needing a full real-world dataset. We use TensorFlow to create a simple synthetic target tensor that represents the true values our model should learn to predict. This tensor is a column of 4 numbers, 3, 5, 7, and 9. It is explicitly defined with a data type of 32-bit floating point to keep numerical operations consistent during training. We check that the input data tensor and the target data tensor have the same shape, so that every input example has a matching target. This alignment is essential for the model to compute the loss correctly during training. If the shapes do not match, it signals a data mismatch that can cause errors and break the training process. We build a simple linear model by defining a single weight value that scales the input data. This weight is created as a variable and is initialized with a random value drawn from a normal distribution. Because its shape is 1 by 1, it represents just one scalar parameter. This scalar weight is then used as the core parameter in our linear model. In our linear model, we use a bias term defined as a TensorFlow variable with a single value initialized to 0. This bias lets the model shift the prediction line up or down so it can better match the data. Because it is a TensorFlow variable, the bias is updated during training, allowing the model to learn the value that best reduces the loss. This function defines the mean squared error loss, a common way to measure how closely a model's predictions match the true target values. It first finds the difference between each prediction and its corresponding target, then uses TensorFlow's square operation to square each of these differences. Finally, it averages all the squared differences to produce a single scalar value that represents the average prediction error across the entire dataset. This function computes the mean squared error by first finding the squared differences between the model's predictions and the true target values, then taking their average using TensorFlow's reduce mean operation. The result is a single scalar that summarizes how closely the predictions match the targets. A lower value indicates that the model's predictions are closer to the true values, which is why this measure is widely used as a loss function in regression tasks. We define a training step function that uses TensorFlow's GradientTape to record the operations needed for automatic differentiation. This recording lets us compute gradients later during optimization. Within this step, the model makes predictions by multiplying the input data by the current weight and then adding the bias. The result is the predicted output based on the model's current parameters. The code computes a loss value using the mean squared error loss function, which compares the model's predictions to the true target values. It does this by taking the difference between each predicted and actual value, squaring those differences, and then averaging them. The result is a single number that summarizes how far the predictions are from the real data. A lower loss value means the model's predictions match the true values more closely, and the model is performing better. The code uses TensorFlow's GradientTape to compute how the loss changes with respect to the model's weight and bias. GradientTape records the operation so it can automatically calculate these gradients. These gradients show how much each parameter should be adjusted to reduce the loss. This information is then used to update the model during training. The code first checks whether gradient clipping is turned on. If it is, it uses a TensorFlow function to clip the gradients based on their global norm, meaning it scales them so their overall size does not go beyond a set maximum value, here equal to 1. By limiting the magnitude of the gradients in this way, the training process becomes more stable. This prevents extremely large updates to the model's parameters that could otherwise harm learning. The learning rate is set to 0.5, which controls how big a step the model takes during each gradient descent update. A larger learning rate can make training faster, but risks skipping past the best solution, while a smaller one is safer, but slower. Choosing 0.5 aims to balance speed and stability, so the model's parameters are updated efficiently without becoming unstable. In gradient descent, we update a weight by subtracting the learning rate multiplied by the gradient of the loss with respect to that weight. This process is repeated to gradually adjust the model parameters and reduce the loss function. The learning rate scales the gradient and controls how big each update step is. By choosing an appropriate learning rate, we keep the updates from being too large or too small, which helps the algorithm move steadily toward an optimal solution. In this step of gradient descent, the code updates the bias by subtracting the learning rate multiplied by the bias gradient from its current value. This adjustment moves the bias in the direction that reduces the loss function. By repeatedly applying this update, the model gradually improves its fit to the data. The code uses TensorFlow's linear algebra tools to compute the global norm of the gradients, which is a single number measuring their overall size across all model parameters. This value summarizes the magnitude of the updates being applied to the weights and biases. By examining this global norm, we can judge how large the training updates are and better understand the stability of the training process. This function returns two values, the current loss and the gradient norm, both converted to standard floating point numbers. It does this by taking their underlying numerical representations and casting them to regular Python floats. Using this conversion ensures they are compatible with other Python operations and libraries. As a result, the loss and gradient norm are easy to interpret, log, and use in further analysis. We start by running a few training steps without using gradient clipping to see how the model behaves when gradients are not limited. A message is printed to indicate that training is proceeding without clipping, making it clear what configuration is being used. During this phase, we manually update the model parameters and watch how the loss and gradient norms change. This helps us understand the impact of unconstrained gradients before introducing any clipping techniques. We start by running a few manual training updates to observe how the training process behaves. For each of 3 steps, we call the training function with gradient clipping turned off, so the gradients are not restricted or stabilized. This lets us see how the model performs when gradient values can grow freely. At each step, the function returns the current loss and the gradient norm, which we then use to judge the stability and performance of the model during these unconstrained updates. This line reports the current training step, the loss value, and the gradient norm, each rounded to 3 decimal places for readability. By printing these values, it lets you monitor how the loss and gradient norm change over time. This helps you track training progress and check the stability of the optimization process at each step. We reset the model's weight parameter by giving it a new random value drawn from a normal distribution using TensorFlow's random initialization. This ensures the weights start fresh for each new training run. Doing this reset is important for making a fair comparison between training with gradient clipping and training without it, because it removes any influence from previous training steps. We set the bias parameter to 0 so that each training run starts from the same initial condition. This makes the comparison between runs fair and consistent. By fixing the bias in this way, we can better isolate and observe the specific impact that gradient clipping has on the training process. We are starting a new training phase where gradient clipping is turned on. In this phase, the gradients are limited so they cannot grow too large, which helps keep the training process more stable. This adjustment can lead to better performance and reliability of the model. A printed message marks the beginning of this phase and indicates that all following training steps will use gradient clipping. We begin by running a few manual training steps to see how the training process behaves. For each of 3 steps, we call the training function with gradient clipping turned on. So the gradients are limited to keep the updates stable and avoid exploding gradients. After each step, the function returns the current loss and the size of the gradients. By tracking these values over the 3 steps, we can observe how the model's performance and stability change during training. This line reports the current training step, the loss value, and the gradient norm, each rounded to 3 decimal places for readability. By printing these values, it allows you to track how the loss and gradient norm change over time. This helps you monitor the training process and understand how the model's learning behavior evolves at each step. This script uses TensorFlow to show how gradient clipping affects training stability. It trains a simple linear model to predict target values from input data, first without clipping, where the loss and gradient norms can fluctuate widely and make training unstable. After resetting the model, it repeats training with gradient clipping turned on, which limits the size of the gradients. With clipping, the updates become more stable and the loss decreases more smoothly. Overall, the comparison illustrates that gradient clipping can prevent excessively large updates and help stabilize the training process. In this lecture, you learned to use tf.GradientTape to compute gradients of scalar losses with respect to TensorFlow variables, interpret gradient values to understand how parameter changes affect a loss function, and implement a simple manual training step using gradients and an optimizer. In the next module, Module 3, we will go over Keras model building.
Thank you for your attention. See you all in the next lecture.